Welcome to this walkthrough of LeetCode problem number 226, Invert Binary Tree. In this problem, we'll explore how to reverse the structure of a binary tree by swapping its left and right subtrees. Stick around to learn both recursive and iterative approaches, as well as their trade-offs. Let's dive in. The problem we're solving is called Invert Binary Tree. The goal is to take a binary tree, represented by its root node, and invert it. Inversion means swapping the left and right subtrees of every node in the tree. The input to this problem is the root node of a binary tree, where each node has three properties: a value, a pointer to its left child, and a pointer to its right child. The output will be the root of the binary tree after all the left and right subtrees have been swapped. This process is also referred to as mirroring the binary tree, and it is typically done recursively by flipping the left and right pointers at each node as we traverse the tree. Let's take a look at the first example to understand this better. Suppose the input tree has a root node with the value 4, and its two children are 2 and 7. The left subtree of 2 contains nodes 1 and 3, while the right subtree of 7 contains nodes 6 and 9. After inversion, the structure of the tree changes. The root node, which is still 4, now has its left and right children swapped. So, 7 becomes the left child, and 2 becomes the right child. Similarly, the children of node 2 are flipped 1 and 3 trade places, and the children of node 7 are also swapped, making 9 the left child and 6 the right child. Here's how the inversion happens step by step. First, the root node, 4, swaps its left child, which is 2, with its right child, which is 7. Then, at the next level, node 2 swaps its left child, 1, with its right child, 3. Meanwhile, node 7 swaps its left child, 6, with its right child, 9. This recursive swapping process continues until all nodes in the tree have had their left and right children flipped. Now, consider another example where the input tree contains only two nodes, a root node with the value 1, and a single left child, 2. After inversion, the root node, 1, swaps its left child, 2, with its right child, which was initially null. As a result, the tree has 2 as the right child of the root, and the left child becomes null. In the second example, we can see how inversion works even in a smaller tree. The root node, 1, simply swaps its left child, which is 2, with its right child, which is null. Now, let's examine the third example. Here, the input tree contains only one node, 1. Since there are no children to swap, the tree remains unchanged after inversion. This illustrates that when a tree has a single node, no action is needed since there's nothing to invert. Now let's consider some important constraints and edge cases for this problem. Node values in the tree can range from -100 to 100, and the input tree may be empty, meaning the root could be null. Additionally, the tree is not guaranteed to be balanced, so we need to handle cases where the tree is skewed, such as when all nodes have only left or only right children. For an empty tree, the output should also be null. For a single node tree, no inversion is necessary since there are no children. Finally, for very large trees with up to 10,000 nodes, we need to ensure our solution is efficient and doesn't run into memory issues, whether we use a recursive or iterative approach. To solve the problem of inverting a binary tree, we essentially need to reverse its structure by swapping the left and right subtrees of each node. One of the most natural and intuitive ways to approach this is through a recursive depth-first search. This method works because the structure of a binary tree lends itself well to recursion. At each node, we can simply swap its left and right children, and then apply the same operation recursively to these children. The steps are straightforward. If the current node is null, we return null since there's nothing to invert. Otherwise, we swap the left and right subtrees. After swapping, we recursively call the function to invert the left and right subtrees of the current node. Once all nodes are processed, we return the root of the inverted tree. In terms of complexity, this approach has a time complexity of O(n), where n is the number of nodes in the tree, since each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, as this is the space required by the recursive call stack. Another approach to solve this problem is the iterative breadth-first search using a queue. Instead of recursion, we use a queue to traverse the tree level by level. This method is particularly useful if we want to avoid the potential stack overflow issues associated with deep recursion. To implement this, we first initialize a queue and add the root node. While the queue is not empty, we process the node at the front of the queue. For each node, we swap its left and right children, and then enqueue these children if they are not null. By doing this, we ensure that every node in the tree is processed and its children are inverted. The time complexity remains O(n), as each node is processed once. The space complexity, however, is O(n) in the worst case, which occurs when the tree is a complete binary tree, and the maximum number of nodes at any level is stored in the queue. A third strategy is the iterative depth-first search using a stack. This approach is similar to the BFS method but uses a stack instead of a queue to traverse the tree. By using a stack, we perform a depth-first traversal, visiting nodes deeper in the tree before their siblings. To implement this, we start by initializing a stack and pushing the root node onto it. While the stack is not empty, we pop the top node, swap its left and right children, and then push the swapped children onto the stack if they are not null. This ensures that all nodes are processed and their subtrees are inverted. The time complexity of this approach is also O(n), as each node is visited once. The space complexity is O(h), where h is the height of the tree, because the stack will hold at most h nodes at any given time in the worst-case scenario of a skewed tree. Among these approaches, the recursive depth-first search stands out as the preferred solution. It aligns naturally with the hierarchical structure of a binary tree, making the code both intuitive and concise. Its time complexity of O(n) is optimal, and the space complexity of O(h) is manageable for most practical scenarios. Additionally, recursion handles the traversal order implicitly, which simplifies the implementation and eliminates the need for extra data structures like queues or stacks. On the other hand, while the BFS and iterative DFS methods are also efficient in terms of time complexity, they require additional memory to store the queue or stack, which increases the implementation complexity. One trade-off of the recursive approach is the potential for stack overflow in cases of extremely deep trees, such as those with a height greater than 10 to the power of 4. However, such cases are rare in typical applications unless explicitly testing edge cases. For its simplicity, readability, and ease of maintenance, the recursive DFS solution is the most practical choice for this problem. The problem we are solving involves inverting a binary tree, which means swapping the left and right children of every node in the tree. For instance, consider the example given. The original tree has a root node with the value 4, and its left subtree contains nodes 2, 1, and 3, while its right subtree includes nodes 7, 6, and 9. After inversion, the left and right subtrees are swapped at every level. The left subtree now contains nodes 7, 9, and 6, and the right subtree contains nodes 2, 3, and 1. This transformation effectively mirrors the tree along its vertical axis, and our goal is to implement an algorithm to achieve this inversion efficiently. Inverting a binary tree involves recursively swapping the left and right subtrees at every node. To achieve this, we use a recursive depth-first search approach. First, we define a base case. If the current node, or root, is null, we simply return null. This ensures that the recursion terminates appropriately and handles cases where the tree is empty or we reach a leaf node. Next, in the recursive step, we swap the left and right children of the current node. After the swap, we recursively call the function on the swapped left and right subtrees. Finally, we return the current node, ensuring that each parent node receives its inverted subtree as the recursion unwinds. This step-by-step approach guarantees that the entire tree is inverted correctly. Additionally, it's important to consider edge cases, such as an empty tree or trees with only one node, to ensure the algorithm handles all scenarios robustly. When dealing with edge cases, if the tree is empty, or the root is null, the function will simply return null. For a single node tree, there's no visible change after inversion, but the algorithm still processes it correctly. The recursive nature of trees makes this problem well suited for a recursive solution, as each node's subtrees can be treated independently. The algorithm essentially performs a post-order traversal, meaning it processes the left and right subtrees before working on the current node. This approach ensures that the inversion is applied consistently throughout the tree. In terms of complexity, the algorithm visits each node once, resulting in a time complexity of O(n), where n represents the number of nodes. However, recursion introduces a space overhead due to the call stack. The space complexity is O(h), where h is the height of the tree. For a balanced tree, this is logarithmic, O log n, but for a skewed tree, it can grow linearly with O(n). Understanding these trade-offs is key to optimizing the solution where necessary. The Python implementation of this algorithm is straightforward and concise. First, we check if the root is null. If it is, we return null immediately, which ensures the base case is handled. Next, we perform the swap operation in constant time, where the left and right child nodes of the current root are exchanged using the line root.left, root.right equals root.right, root.left. Then, we recursively call the function on the left and right subtrees, processing each child node in the same way. Finally, we return the root node after its subtrees have been inverted. This simple yet effective implementation leverages the recursive nature of the problem to handle the inversion efficiently. The key operation here is the node swap, which is performed in O(1) time for each node, ensuring that the algorithm remains efficient. Recursively traversing the tree through calls like invert tree, root.left, and invert tree, root.right, ensures that each subtree is processed independently, and since every node is visited exactly once, the traversal takes O(n) time. Returning the current node after processing allows the tree to be reassembled as the recursion unwinds. Additionally, we can optimize this solution further by considering an iterative breadth-first search approach using a queue. This avoids the risk of stack overflow in cases of very deep trees, as it doesn't rely on recursion. The algorithm works in place, directly modifying the input tree without the need for extra memory to create new nodes. Lastly, it's important to verify the algorithm against edge cases, such as null trees, single-node trees, skewed trees, and balanced trees. Each of these scenarios highlights the versatility and robustness of the solution. For example, a null input should immediately return null, while a single-node tree should remain unchanged after inversion. Skewed trees should be handled efficiently without unnecessary operations, and balanced trees demonstrate the full impact of the inversion process at every level. This Python implementation solves LeetCode problem number 226, invert binary tree using a recursive depth-first search (DFS) approach. First, we define a tree node class to represent the structure of a binary tree node. Each node has a value, a left child, and a right child, which are initialized in the constructor. This is the standard definition for binary trees in LeetCode problems. The invert tree function is implemented within the solution class. This function takes the root of the binary tree as input and returns the root of the inverted tree as output. Let's break down the steps. 1. Base case check. If the input root is none, i.e., the tree is empty or we reach a leaf's child, the function immediately returns none. This serves as the termination condition for the recursion. 2. Swap operation. The left and right children of the current node are swapped using Python's tuple assignment, root.left, root.right equals root.right, root.left. This is the core operation that inverts the tree structure. 3. Recursive calls. After swapping the children, the function recursively calls itself on the left and right subtrees to invert them further. This ensures that the entire tree is processed, one node at a time. 4. Return statement. Once the entire tree is inverted, the function returns the root node of the modified tree. This approach has a time complexity of O(n), where n is the number of nodes in the tree, because we visit each node exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive stack used during the DFS traversal. For a balanced tree, this is O log n, but in the worst case of a skewed tree, it can be O(n). The code is concise and leverages recursion to handle the tree inversion cleanly. It is also robust against edge cases, such as an empty tree or a tree with only one node, as the base case ensures proper termination. Here, we start by defining the structure of a binary tree node with the treenode class. Each node has an integer value val and two child nodes, left and right. We provide three constructors, one with no arguments, one that initializes just the value, and another that initializes the value along with its left and right children. Now, in the solution class, we define the method invertTree, which takes the root of the binary tree as input and returns the root of the inverted tree. The first thing we handle is the base case. If the root is null, meaning the tree is empty or we've reached a leaf node's child, we simply return null. Then, we prepare to swap the left and right children of the current node by temporarily storing the left child in a variable called temp. Next, we assign the right child of the current node to its left child and the value stored in temp to its right child, effectively swapping the two. After the swap, we proceed with a recursive approach to invert the left and right subtrees. By calling invert tree on root.left and root.right, we ensure that the inversion process is applied to all levels of the tree. Finally, we return the root node, which now represents the inverted tree. This approach is straightforward and leverages recursion to traverse the entire tree, swapping child nodes at each step. The result is a fully inverted binary tree. Let's begin with a simple binary tree example. Here, the input tree has a root node with the value 1, and it has 2 children, 2 on the left and 3 on the right. We start by focusing on the root node, which is 1. The first step is to swap its left and right children. After the swap, 3 becomes the left child, and 2 becomes the right child. At this point, the tree structure looks inverted at the root level. Next, we move to the left child of the root, which is now the node with value 3. Since this node has no children, there are no further swaps to perform here. The left and right references for this node remain as none. This completes the processing for the left subtree of the root. Now, we return to the root and process the right child, which is the node with value 2. Similar to the left child, this node also has no children, so no swaps are performed. The left and right references for this node remain as none. At this stage, the entire tree has been processed, and the final inverted tree structure is complete. The root node 1 now has 3 as its left child and 2 as its right child. This inverted tree is then returned as the output. Moving forward, we will explore a larger binary tree to understand how the process works with more complex structures. In this example, the input tree has a root node with the value 4, and it has 2 children, 2 on the left and 7 on the right. The left subtree of 2 further contains nodes 1 and 3, while the right subtree of 7 contains nodes 6 and 9. We start at the root node, 4, and the first step is to swap its left and right children. As a result, 7 becomes the left child, and 2 becomes the right child. The tree now reflects this initial inversion. Next, we move to the left child of the root, which is the node with value 7. Here, we swap its children as well. After the swap, 9 becomes the left child, and 6 becomes the right child of node 7. This completes the inversion for the left subtree of the root. Now, we focus on the individual children of node 7. Node 9 has no children, so no further swaps are needed. Similarly, node 6 also has no children, so no swaps are performed here either. With the left subtree fully processed, we return to the root and shift our attention to the right child, which is the node with value 2. Here, we perform a swap of its children. After the swap, 3 becomes the left child, and 1 becomes the right child of node 2. Finally, we process the individual nodes 3 and 1. Since neither of them has children, no additional swaps are necessary. At this point, the entire tree has been inverted. The root node 4 now has 7 as its left child and 2 as its right child, with their respective subtrees also inverted. This completes the process for the larger binary tree. Now, let's examine an edge case where the tree contains only a single node. The input tree consists of just the root node, which has the value 1. Since this node has no children, there are no swaps needed. The left and right references for this node remain as none. As a result, the tree remains unchanged. The output is the same single node tree, and it is returned as is. This example demonstrates that the algorithm handles edge cases like single-node trees gracefully without performing unnecessary operations. To summarize, the solution uses a recursive approach to traverse the binary tree and invert it subtree by subtree. At each node, the left and right children are swapped, and the function is called recursively on these children to repeat the process. The base case for the recursion occurs when the current node is none, in which case the function simply returns none. The time complexity of this solution is O(n), where n is the total number of nodes in the tree, since each node is visited once. The space complexity is O(h), where h is the height of the tree, as this accounts for the recursive call stack. By applying this technique, we can efficiently invert any binary tree, regardless of size or complexity. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This is because the function, invert tree, processes each node in the tree exactly once. For each node, the operation of swapping its left and right children is an O(1) operation. It takes constant time. Additionally, the function makes two recursive calls, one for the left child and one for the right child, ensuring that all nodes in the tree are eventually visited. Since there are n nodes in total, and each node takes O(1) time to process, the overall time complexity becomes O(n). Importantly, this holds true regardless of the tree's structure, whether it is balanced, unbalanced, or even completely skewed. In all cases, every node is visited, resulting in a consistent time complexity of O(n). Next, let's examine the space complexity, which is determined by the memory used for the recursive call stack. The depth of the recursion corresponds to the height of the binary tree, denoted as h. In the best-case scenario, if the tree is balanced, the height is approximately log n, leading to a space complexity of O log n. However, in the worst-case scenario, such as a completely skewed tree where all nodes form a single branch, the height of the tree can reach n. In this case, the space complexity becomes O(n). Each recursive call adds a frame to the call stack, consuming O(1) memory per call for storing local variables and pointers. The maximum number of calls on the stack at any point is equal to the tree's height, which is why the overall space complexity is O(h). Now, comparing this solution to a brute force or naive alternative, we see clear advantages. A brute force approach might involve constructing a new binary tree by traversing the original tree and inserting nodes in inverted positions. While functional, this would require additional memory to store the new tree structure, resulting in a space complexity of O(n). In contrast, our solution modifies the tree in place, minimizing space usage. It's worth noting that both approaches share the same time complexity, O(n), since all nodes must still be visited. To summarize, the recursive traversal in our solution ensures each node is processed exactly once, with each operation taking O(1) time, giving a total time complexity of O(n). The call stack depth, proportional to the tree height, determines the space complexity, which is O(h). For balanced trees, this is O log n, while for skewed trees, it becomes O(n). This makes our approach both time and space efficient for in-place tree inversion. When working on recursive solutions for inverting a binary tree, one common mistake is forgetting to include the base case. The base case is crucial because it tells the recursion when to stop. For instance, if you don't handle null nodes properly by returning none, your program might end up in infinite recursion, leading to a crash. Another common issue is not swapping the left and right subtrees correctly. The order of operations here is important. If you overwrite one child before saving its reference, you lose that data. Always store references to both child nodes first before performing the swap. For iterative approaches like DFS or BFS, it's easy to forget to push the swapped children back onto the stack or queue, which can result in incomplete traversal. Lastly, don't overlook edge cases. An empty tree, a tree with a single node, or trees with only left or right subtrees are scenarios that can cause runtime errors if not explicitly tested. These edge cases should always be part of your test plan. Inefficient memory usage is another issue to watch out for, particularly in recursive solutions. Recursive calls consume stack space, and in an unbalanced tree, the stack depth can grow to O(n). Make sure to include this auxiliary space in your complexity analysis. From an interview perspective, this problem is often used to evaluate your understanding of tree traversal techniques such as DFS and BFS. Interviewers might assess how well you manipulate tree structures or how clearly you explain recursion. Be ready to discuss both time complexity, which is O(n), and space complexity, including the stack space for recursion, which is O(h), where h is the tree height. You might also encounter follow-up questions asking for variations, like returning an inverted copy of the tree instead of modifying it in place, or applying the same concept to graphs. Clear communication of your thought process is key, particularly for recursive approaches, as they can be challenging to grasp at first. This problem shares concepts with several related problems, which can help you recognize patterns and broaden your understanding. For example, LeetCode 100, same tree, asks you to determine if two trees are structurally identical. LeetCode 101, symmetric tree, challenges you to check if a binary tree is a mirror of itself. LeetCode 104, maximum depth of binary tree, focuses on finding the height of a tree, and LeetCode 617, merge two binary trees, involves combining two trees by summing their node values. Considering alternative approaches, recursive DFS is often the go-to for its simplicity and alignment with the natural structure of tree traversal. However, it has the drawback of stack overflow risks in very deep or unbalanced trees. Iterative BFS, on the other hand, avoids recursion and is safer for deep trees, though it requires extra memory for storing the queue, which in the worst case can grow to O(n) for a full binary tree. Another alternative is iterative DFS, which uses an explicit stack to control the traversal process. This approach offers similar advantages to recursive DFS, such as depth-first ordering, but eliminates the risk of stack overflow from recursion. However, managing the stack manually introduces its own challenges. The code can become less readable and more prone to errors compared to the cleaner recursive solution. While each approach has its pros and cons, selecting the right one often depends on the constraints of the problem, the size and structure of the tree, and the resources available. Understanding these trade-offs will not only help you solve the problem efficiently but also demonstrate your ability to make informed decisions during interviews. Great job reviewing the invert binary tree problem. We covered the recursive and iterative approaches, along with their trade-offs in terms of simplicity and space usage. Remember, mastering tree traversal techniques will serve you well in many coding problems. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!